We've done the case where light bends through a flat interface between two materials with different indices of refraction. What about the case of light going through a curved surface, like from air inside a spherical plastic ball or glass ball, or light going from air into a spherical fish tank or something like that? So let's go and draw a curve here. And instead of just being a curve alone, it's separating two materials, N1 and 2. So this might be a ball of glass, and N2 would be 1.5, and this would be air of 1. But it could be a ball of glass and water, or a ball of water and surrounded by glass, or whatever it is. Okay. So just like our lens tracing, we're going to define an optical axis here. Okay. And this surface has a curvature, a radius, radius r, and it's only one surface, so that's the only curvature descriptor we have, is the radius of that surface. So if I have an object over here on the N1 side, and light from the room, or if it's outside the sun, reflects off of that in all sorts of directions, and many of those rays go through the surface, well, by Snell's law, they're going to refract through the surface, and we will get image formation. Okay. Now, I'm going to draw another radial line. Do it about right here. Okay, that's a radial line, which I'm going to extend further out. And something about radial lines, which I may not have drawn very good here, is that they're perpendicular to the surface. So if I have a light ray that hits that surface right there, then by Snell's law, it's going to bend towards the normal. So it's going to bend towards this. And it's going to come down here, keep going. Alright? And this would be my theta 1. And this would be my theta 2 from Snell's law. Okay? Now, I could keep doing that at all sorts of positions along this, and those rays would converge at that point, or some point over here. Okay, and I would create an image somewhere over here. All right. Now, that's a lot of math. That's a lot of geometry. And let me kind of skip to the chase, and we'll use some good physical descriptors to understand what the result tells us. What it ends up giving by doing all the careful geometry there is that N1 over S1, okay, S being the distance from the surface to, or sorry, just S, I apologize. S being the distance from the surface to the object, plus N2 over S prime being the distance from the surface to where the image forms, okay, equals N2 minus N1 over R. Okay. That's the result of all the algebra that you would need to do, all the geometry that you'd need to do, as well as using small angle approximation to be able to find out how far the image would form based on the object being over here. Okay? So, that's great. It's a formula. It's pretty complex to derive, therefore we're going to take it as kind of fundamental. But what's more important is understanding what it means. Okay? So, for example, we know that curvatures have positive or negative curvature, diverging lenses versus converging lenses. How do we know what's going on here? There's a really good rule that I have found can be used to determine the signs for every optical situation. One rule, applied carefully, but one rule, instead of having to memorize a whole bunch of signs conventions for converging mirrors or diverging mirrors, or a surface between two materials, or whatever the case may be. There's one rule that works all the time. And the idea I like to say is light really going there? Okay? Is light really going there? Okay. So, for example, is the radius of this curved surface positive or negative? How do we know? Well, the way we know is when the object's over here, light's coming off the object, hits this lens, and goes this way. It doesn't bounce off. Okay? Light really does go over in this direction. That would make this radius, okay, positive. So this, in this case, this would be positive. Alright? Now, if I had the case like this, and the radius is now over here, and I have my object over here, so it's inside. Alright? If it's inside, now the light hits this surface and continues out this way. Alright? But the radius is on this side. So the light, after hitting the surface, goes this way. Therefore, in this case, the radius is negative. Okay. Now, light's always coming off the object, so S is always positive. Okay, and then the indices of refraction are also positive. They don't adjust because of the surface. So it's really just this R that could be positive or negative, which means that S could end up being positive or negative depending on these values. The other thing to check is what is N1, what is N2? N1 is the material index where the object is. Where is the light coming from? Okay, so this is the in this case this is N1. You know, if this is air to water, this would be 1, and N2 is where the light went through. Okay, in this case, the N1 is again on this side. It's associated with the object. So if this was a glass bulb, and this would be 1.5. If this was in air, that'd be 1. So N1 is associated with where the object is. N2 is the other side. And be careful not to say just where the image is, because sometimes the image can end up different on the same side as the object. Not necessarily in this case, but sometimes it can. Okay. So this is just where the object is, and this is the other material. This is positive if it's on the other side of the surface from the object. It's negative if it's on the same side of the surface. Or in other words, light is really going there, and light is not really going there.